So, limits. Let C and L be real numbers. The function f has a limit L as x approaches C. If given any positive integer epsilon, there is a positive number delta such that for all x where x minus C is between 0 and delta, then the absolute value of the limit of f of x minus L is equal to epsilon. You don't really have to know that for posterity. So if you're writing that one down, stop. Here's what you absolutely need to have. You need to have this. That is where we are working with limits. The formal definition, although nice, is confusing. And I never will ever bring up the formal definition of a limit ever again. Mr. Round likes to talk about it. He likes to do the proof. I'm sorry, I don't need to. I'm not going to do it. That's not worth it for me. And that's fine. There are things I know that I do that he doesn't do. It's just, it is what it is. All teachers are that way. But here's what's important when we're talking about limits. There we go. Move this up higher. Okay. The limit as x approaches C. The limit as x approaches C. Not as x is C, but as x approaches C. Of the function f of x is L. It's a numerical value. If it exists, it is a numerical value. L is a numerical value. So I have a function, and I put in values of x that get closer and closer to a particular number. What does y go towards? This is a y value corresponding with, as my x is closer to a particular value, what y value do I approach? Okay. So, what is a limit in terms? Somebody who knows calculus would understand. Actually, let's do that. A limit is the expected y value a function reaches. So as my x coordinate approaches a particular value, what does the y value approach? As x heads towards a particular number, what is the y value corresponding with that? Okay. When does a limit exist? Limit exists from the left and right hand limits exist or equal. You can do one-handed limits, or one-sided limits, I should say. And the limit from both directions have to be the same thing. So when I have graphs up here, you do not have to have detail. You do have to have the points, and you have to have an idea. So draw an xy coordinate. You have one important point. It's at 0, 1. Put a hashtag. Put the slash across the one and put a dot there. Have a line coming down. The line coming down. That's good enough for what your graph on your notes should be. You do not have to have the detail that I have here. Okay. So, a lot of notation today. A lot of notation. From the left. Which direction is left? As you are looking at this graph, which direction is left? That right, from the negative side. So when I come from numbers smaller than what I'm approaching. So the limit as x approaches 0 from the left, the little negative up here means it's from the left. It's kind of hard to see when you're in the cheap seats. But there's a little negative sign there. It's not an exponent. It is not an exponent. What that says is I'm approaching 0 from the left. That means I'm coming from numbers smaller than 0 towards 0. I'm taking values of x smaller than 0 and plugging them in repeatedly into the function, getting my y-coordinate. As I approach 0 from this side, what does my y-coordinate approach? That's what this arrow is demonstrating here. I'm moving along this line. X-coordinate's going in here. What is my corresponding y-coordinate? As x goes towards 0, what y value do I approach? 1. It goes towards 1. It actually hits 1, but that's not necessary. It approaches 1. So the limit as x approaches 0 from the left of f of x is 1. Okay. when I do it from the right. And instead of a little negative, I've got a little positive. So I'm taking the limit as x approaches 0 from the right, which means I'm taking numbers larger than 0 and plugging them in, getting closer and closer to 0 from the right-hand side. 2, 3, 1, 1/2, 1/4, 1/8, and so on and so on and so on. I'm getting closer and closer to 0 from numbers starting with numbers larger heading towards 0 from that side. And it's the same thing. As my x values go towards 0, what does my y value go towards? So I move along the line, it goes towards 1, so my limit's 1. Yes?
It's always like the y and stuff that it's like...
No, it's not always. We'll get to more examples as we come up. Now here's the important thing under this one. As I approach from the left and I approach from the right, do they go towards the same value? So that means the limit, and I'll have to extend this. Come on, there we go. So the limit as x approaches 0 is 1, because from the left-hand side and the right-hand side, I go towards the same thing. The limit from the left and the limit from the right are the same limit. Therefore, the limit as I approach 0 is 1. This implies it goes towards it from both sides. Yes? The negative and the positive sign are strictly telling me which direction I'm going on the limit. Yeah, you won't ever see that anywhere else other than the limit notation. It is not an exponent. It is strictly telling you which direction you're going. If you don't see one, if you don't see a plus or a minus, what's it doing? Coming at it from both sides. Okay? So you have to know, is it coming out from both sides? Muy importante. Muy importante. Get this down. Okay? A limit of a function f of x exists if, what does that stand for? If and only if the right-hand limit and the left-hand limit are the same. You need to know this notation. The limit, if the limit is of x as x approaches a from the right of f of x equals the limit as x approaches a from the left of f of x, and they're both equal to each other and they're equal to L, then the limit itself exists and it is that limit L. Just like what we did in the previous example. Went towards 0, they both had a limit of 1 coming from the left and right. So the limit as we approach 0 is 1. This notation is important. You will have questions, homework, tests, AP tests. Knowing this is important. Knowing where does the limit exist. Because you'll ask, is there a limit? And you have to say, yes, because from the left and the right, it's the same thing. If you don't say left and right, I've seen 3 or 4 AP test questions the last few years where they specifically say 1 point if using left and right hand limits, and 0 if not. So you must mention in your work that you're doing left and right hand limits. And if you don't get the points. There might be 3 points, and they'll do this. It's worth 1 point for this and 1 point for that. Note, 0 out of 3 of no right and left hand limits. Yeah, they will do that. They will say, if you do not have that fundamental thing. Okay, this note down here at the bottom is also extremely important. The function itself does not have to exist in order for the limit to exist. It's the number it approaches, it's not the number it is. It's the number it approaches, it is not the number it is. The function may not exist at the place you are taking the limit, But if it goes towards that point, there is a limit. It's what it goes towards. It's what it approaches. It is not its specific value. It is entirely possible that your function does not exist at the place you have a limit. Okay, that's an important thing to understand. It doesn't actually have to exist at that point. Okay, it doesn't actually have to exist at that point. Okay. Everybody have this down? Okay, so here's what I want you to do. In your notes, I strongly suggest you sketch this out. Make sure you have a sketch of this graph and answer those questions. What is the limit as it approaches 1 from the right, 1 from the left, 1 itself, and what is the function at 1? Okay, we're back on. So, approaching 1 from the left. So as x goes this way, what's my y value I approach? -2. As I go this way, what is the y value I approach? -2. So, the limit as x approaches 1 from the left of f of x equals the limit as x approaches 1 from the right of f of x. So therefore, the limit as x approaches 1 is -2. What is f of 1? Does not exist. D, N, E does not exist. The limit and the function do not have to have the same values. And this is not the only time where that happens. You can have a function that has a coordinate that exists, but that's not what it approaches from there. Yes? No, it does not exist. It's not undefined. It does not exist. There's a difference between the two. There is a difference between undefined and does not exist. Good question.
So can you explain that one way? Is it just because it's an open circle?
Yeah, because there's an open circle. There is no y value. There is no value for the function at that point. It does not exist because there's no value for that function. It's an open circle. It doesn't exist. There's a gap. There's a hole. So if I've got a little ant running along my graph here, it's got to jump the gap to get to the other side. It can't follow along the trail. Okay, it doesn't exist.
So if there were a point in the function that like
If there was a point, and I'm not sure if we do this later or not, but let's say there's another coordinate here. So let's say it's at 0, then the function could be 0, and the limit exists and the function exists, but they're not equal to each other. That's okay too. Equaling each other is an important thing for later on. Again. Okay. So the limit as x approaches -3 from the left. So as I move along here, what's my y value? 3. As I approach from the right, going this way, what is it? 6. And the limit as x approaches 3 from the left of f of x does not equal the limit as x approaches 3 from the right of f of x. Therefore, the limit as x approaches 3 does not exist. Right-hand limit's good, left-hand limit's good, but they're not the same. What is f of 3? 3. So you can have a function exist without having the limit exist. Okay, the function can exist just fine without the limit. There is one other time where you use right and left-hand limits other than coming at it from both directions like that. There are times, and we will talk about them, is that the function's only one-sided. It ends at a certain point. Rather than talking about domain of everywhere, we have a limited domain that goes from A to B. We approach A from the right, we approach B from the left, because the left-hand side of A doesn't exist and the left of B doesn't exist. One side of the limits are good enough to say the limit exists at that point, but that's because the function itself does not exist outside that realm. These are not those examples, but we will have those later on. Okay. Questions? Yes.
So does it not exist because like they're not?
They're not the same.
Oh,
They're not the same. They don't go to the same point from the left and the right. Left and right have to be equal, or the limit itself does not exist.
thank you.
Okay, properties of limits. If capital L, capital M, then L and M will be what the limit is. X and K are constants, or sorry, C and K are constants. And the limit as X approaches C of F of X is L, and the limit as approaches G, X approaches C of G of X is M. So the limit of F is L, and the limit of G is M as they approach the same X coordinate. So two functions going to the same X coordinate. Our rules are as follows. The limit as X approaches C of F of X plus G of X is the limit of F plus the limit of G. So the limit of two functions added going to the same point is equal to the limit of the first function plus the limit of the second function. It doesn't always work for everything you do. What you do to two functions that are added is not always what you do to the first plus what you do to the second one. Okay. So this is the sum rule. This is the difference rule. If you subtract the two functions, it's the limit of the first minus the limit of the second. So the limit of two functions subtracted is the limit of the first minus the limit of the second. Generally speaking, but not always. Remember, things don't always go both ways with addition and subtraction. Remember, addition is commutative. Subtraction is not. 2 plus 3 is equal to 3 plus 2, but 2 minus 3 is not equal to 3 minus 2. Doesn't work necessarily going both ways from addition and subtraction. The limit of a function f times a function g is the limit of f times the limit of g. This is really not going to apply a lot of any other place other than here in this class. It does not. And I'm warning you now because that's probably one of the biggest mistakes I see later on when we do other similar rules. Is that, oh, well, the limit of adding is added, the limit of subtracting is subtracted, multiplying is going to be multiplied. No, that one really ends here. That only applies with limits. It doesn't apply to anything else we do other than limits in here, pretty much. Just warning you. Trying to give you a heads up so you don't screw things up later. The limit of a constant times a function is that constant times the limit. So to kind of illustrate this one, if I have, let's say, the limit of 3x, well, that's equal to 3 times the limit of x. I can pull that constant out and find the limit, and that might be easier. Okay, there are times pulling a constant out will make your life a lot easier because then you don't have to worry about it and just stick it back on when you're done doing your work. Okay, that is a very useful tool. Not always, but often. And last but not least, the limit of a function f of x divided by g of x is the limit of f divided by the limit of g as long as the limit of g is not 0. Your denominator should ever be 0. What this technically does is it lets us take something that is very complex and break it down into simpler parts. These rules let us take, hey, we've got this and this. We can split them up, or we can bring them together if we want to bring them together. We can do that. If we have two functions that are added and we don't want to do them individually, we can put them together and then do them as one. We can do that. So far, all we've done and we still got more on the notes, just don't want to forget to hand these out. We've done things graphically. What does the picture tell us? You need to understand how to interpret graphs. We're going to do a lot of graphical interpretation. And this is just the beginning. Bless you. Hey. You will love working with polynomials. Polynomials are the easiest functions to work with, except for maybe constants. Well, this is a short chapter, by the way. Your chapter test will be I think 2 weeks from today.
Today, Friday.
Today is Friday. There will be a quiz next week. I think the quiz will be Wednesday next week, yeah. Okay. So, now we're going to work things algebraically rather than off of a graph. So, pretty much as long as my function exists, as long as I don't have any issues plugging the value in, I can just plug the value in. Polynomials are great because you can do anything you want to a polynomial and not really worry about anything going on with it. You'll love polynomials because you can just slap things in there. It doesn't matter. You don't have to worry about domain and range issues. You really generally don't have to, particularly domain issues. So just plug it in. 2 cubed plus 4 times 2 squared minus 3. 8 plus 16 is 24 minus 3, get 21. So the limit as x approaches 2 of x cubed plus 4x squared minus 3 is 21. Easy peasy. Like I said, you'll love polynomials. You just plug it in, you can just do substitution, no problem. Okay? Questions? Okay. If I plug 2, if I do this one, if I do this one, I will get 0 in my denominator. The function does not exist at x equals 2. Does that mean the limit does not exist? No, the limit could still exist. So what do? You try to simplify it first, and then see if you can plug the values in. The limit as x approaches 2. Oh, okay, 2x, x, 1. Is that right? No, it's 2. That's 2 here. 2, 2, 4. Minus 1, minus 2. There we go, right? Check my factoring. I didn't work this out ahead of time. You will need to be really good at factoring. Does that work? Does the factoring work on that one? It's a 1. So it's 2x minus 1, x minus 2. So that gives me negative 4. It gives me negative 4x, negative 1x. That gives me 5x. I'm good. Okay. So most likely one of those factors will be a factor of my denominator as well. Most likely the factor that's going to be in my denominator is the one that is screwing me up on plugging in 2. So most likely one of my factors is x minus 2. Which means it has to be 5x plus 3. Double check to make sure that works. I get 5x squared, I get negative 6. Negative 10x plus 3 gives me negative 7x for my middle term. I'm good.
Wait, so how did you know it was x minus 2?
I use this as a hint.
Okay.
It doesn't exist at 2, which means most likely the thing that's causing me a problem is the factor that will give me 0 in my denominator with 2. So what do I do now? I can get rid of those. And I can take the limit as x approaches 2 of 2x minus 1 over 5x plus 3, which gives me, if I put 2 in there, that's 4 minus 1, I get 3. 10 plus 3, 13ths. So my limit exists, I just have to do a little algebra. These are the second easiest ones. You ready for some fun?
Oh,
Get ready. Get ready. Put your head on. Okay. Can I just put in 0? No, because I'll get 0 in my denominator. Okay, crap. So here's what I have to do. I gotta work this problem out. See if I can maneuver it around, change things around. My first thing is when I see trig functions that are not sine and cosine, I make them sine and cosines. The tangent is sine over cosine. So this is equal to the limit as x approaches 0 of sine x over cosine x times 1 over x. Correct? You see where that happens? Because sine x, cosine x is tangent. Tangent times 1 over x is tangent over x. Same thing. Right? They are equivalent terms. Okay. This still doesn't work. So I still have 0 in my denominator. However, I have a trick up my sleeve that you will like and you will want to remember because it is extremely useful. Sine of x over x times 1 over the cosine of x. All I did was take my multiple fractions and I just moved the numerator to the denominators. Actually, all I did was move the denominators, which works, right? It's multiplication. It's not a big deal. Okay, multiply, and I can switch my multiplication. And you're thinking, okay, that's an x on the side, sine x. No, y has not been introduced. Okay. And I know what you're thinking. You're thinking, but Mr. Orris, you still have 0 in the denominator. You still can't do that. Okay, we'll come back to that one. Let's look at the 1 over cosine of x. Can I put 0 in here? What's the cosine of 0? 1. So what does this equal? That's 1. Now, here is a piece of knowledge that I am going to give to you that you will need to remember. The sine of a number very close to 0 is equal to what we're taking the sine of. So if x is really close to 0, the sine of x is almost exactly the same value. And if you look at a graph of a sine function, as it approaches 0, what does it approach? It approaches 0. 0 approaches 0. The x and y coordinates go to the same place. Okay? The sine of very small angles is equal to the measurement of that angle. So, although this does not exist at 0, but when I put x in 0, this approaches 0. This approaches 0. If I am approaching the same number from if the top of my fraction and the bottom of my fraction are going towards the same number, because remember, it's not what it is at 0, it's what it approaches. And if the numerator and the denominator are both approaching the same value, what is that a fraction approaching? 1. Because what is anything over itself? 1. And if the numerator and the denominator are heading towards the same value, we're heading to the same thing over itself, which is 1. So the limit of this is 1. No, I didn't make it 0. I approach 0. And this is the key. This is what screws everybody up with limits. To go, but it doesn't exist at 0. I don't care what's happening exactly at 0. I care what happens if I get close to 0. Hey, got a big open hole in the ground? I'm all right as long as I don't actually step in the hole. I can get up really close. I care what's happening as I'm getting close. I'm not stepping in the hole, but I'm going to get right up to the edge. I'm okay at the edge. So as I get close to the hole, I'm okay. And I don't care what's going on at the hole. I care what's happening as I get close to the hole. Does that make sense? That's why it's the limit as x approaches 0. This is not 1 itself, but the limit is 1. This is not 1, but the limit is 1.
So can it get closer than 1?
Guys, what?
Can it still get closer from that 1 to the 0? Though?
No. It will approach 1. It will not ever be 0 because I'm not actually getting to 0. And technically at 0 it's undefined. Technically this is undefined at 0. But I don't care what's happening at 0. I don't care what's going on at 0. 0 is like on the other side of the wall, but I'm going to get as close to that wall as I can get.
What about like 0.1?
0.1 is still not 0.
Oh, so we could write
You can get closer and closer. You can get even closer now.
0.001.
0.001, 0.00001. It doesn't matter as long as I'm not actually at
So is
0.
that acceptable here if we just put a point?
No, put 1. It's 1.
Forgot about 1. Sign. That's the sign. That's the same thing as itself.
Yeah, you are confusing
Oh, so it'd be point whatever. Yeah.
the limit
Okay, I get it.
of the sine of x over x is not equal to the sine of x over x as x approaches 0 at x equals 0. They're not the same value, but the limit approaches 1 where that is undefined. Remember, the limit and the function do not need to be the same value. You can have a limit exist without a function. Now, so this is tangent of x over x. Now, it shows it existing at x equals 0. But we know that this original function does not actually equal 0. That's one of the things I don't like about Desmos. Is if you've got a hole in the graph, I can zoom in on this as much as I want to zoom in. It will never show a hole in the graph. It will never do that. It's one of the few things I really don't like about Desmos is that there's a point of discontinuity in the graph. It does not give you that point of discontinuity. Graphmatic, I think, does. I think it does. And I'm going to get a copy here, and we're looking to actually get a copy so we can put it in the lab so we may be able to do a few things together, which would be really cool if we can do that. I'm waiting because I'm supposed to get a new computer, and I don't want to get a new computer and then have everything get screwed up when I try to transfer the program over and have to reinstall and all that other stuff. Because I won't really need it for another month or so at least, before the Graphmatic is better than Desmos. So, but I remember, I don't really care. I don't know what's going on here. I don't have to know what's going on right there. I want to know what's going on as I get close to it. What does it get close to? It gets close to 1. I don't really care what's happening at that point. I care what happens as I approach that point. The limit is as I approach the value, not what is happening at that value. Okay. Now, when all else fails, and this is a when all else fails situation, you can make a table of values and plug in values that approach from the left and from the right the number you are approaching. Take a second, copy down the table. Okay. So these two columns here, this half is as x approaches 0 from the right, because these are all numbers larger than 0, but they're getting what? Getting closer to 0. So these are values as it approaches 0. So if I put 0.1 into the absolute value of x over x, I get 1. If I put 0.01 in there, what do I get? I get 1. If I put 0.001, 0.00001, 1. So I could say that the limit as x approaches 0 from the right of the absolute value of x over x is 1. I figured out my right-hand limit by using the left-hand side of that table. If I go to the right-hand side of the table, I can find my left-hand limit. I put negative 0.1 in there. What do I get? Negative 1, negative 0.01, negative 1, negative 1, and let's end the suspense, it's negative 1. So the limit as x approaches 0 from the left-hand side of the absolute value of x over x equals negative 1. So does the limit as x approaches 0 of the absolute value of x over x? It is what? Does not exist because those two are not equal. But if nothing else, you can put in a table of values and approach putting in ones that are closer and closer and closer. What do these numbers get close to? This one's kind of misleading because it's the same value all the way. But if this is not the same value, but they're headed towards a particular value, then you get the idea of what a limit is. Okay? Any questions on that? This will always work. I would suggest you actually do this on something other than something simple like this. You use numbers that actually get a little smaller than that, personally. But like I said, it depends on which one you do. Okay, one more. And then the sandwich theorem. The sandwich theorem. The sandwich theorem. Now, I will be honest with you. You're only going to see the sandwich theorem, I dare to say, one more time. Your homework. But I really like it. It's a cool idea. It's a cool concept to talk about. Okay. It will not be on my chapter test, and I don't think it's part of what AP wants you to be tested on. But it's a nice concept. It's an important concept. I like to talk about it. Okay, sandwich theorem. We sandwich a function between two functions with known limits equal to each other. So here's the deal. Sandwich theorem says that if a function f of x is between g of x and h of x in some interval containing point C, where I'm taking my limit at. Okay, so if I have, here's f. Actually, let's make it a little easier than that. So here's f. Here's G, and here's H. But to be perfectly honest, I don't know what's going on in the middle. I don't know what's going on at this point C. I don't know what's going on there. But as I go towards C, G is above and H is below. So I go towards C from the other way. G is above and H is below. F is between those two functions as I'm getting close to it. Now, way out over here, they might crisscross each other several times. Same thing. Once I get past here, I don't know what the hell's going on. I don't care. It's in that immediate vicinity of what's going on. And that immediate vicinity might be 1/10,000th of a width apart, and we care about what's going on in the middle. Or it could be anywhere from like 10 million to negative 10 million. We don't know. We don't know that interval, but we care about what's going on right in the middle of that interval on both sides of that point. One's above, one's below at all times. Once we get outside the interval, we don't care what's going on. And we don't know what's going on exactly inside there. But exactly inside there, that little width, exactly inside there, is some teeny tiny little point. It's at that particular point, right up before it, right up afterwards, it's between the two. So that means the limit of the upper function is equal to the limit of the lower function. So if the one on top approaches a point, and the one on the bottom approaches a point, and the one in the middle is in the middle, where does it go? It goes to the same point. What this is used for is if you can't find the limit, it's very, very difficult to find the limit of the one in the middle. But you can find one above and work them and show that they go to the same point. Therefore, the one in the middle has to do that. If you try to compute this limit, it's not going to happen. It's extremely difficult to do. Extremely difficult to do. Okay. What you end up with is, and if you graph it, if I recall, as it approaches, it starts doing all this squiggly crap in the middle there. You can't even tell on a graph what's going on. The only way we can do it is find a function above and a function below. I do believe. Nope, it's not there. Sorry. But I can find a function above and below. As x squared approaches 0, what is x squared? What is the limit as x squared approaches 0? It would be 0. All of those reasons. So as it approaches 0, you're good. Now, here's the thing. As I approach it from above and approach it from below, if I look at x squared and negative x squared, positive, negative. Actually, I need to work this around the other way to make my thing work. Negative x squared. This is always negative, right? So it goes towards 0. This is always positive, but goes towards 0. Between the two. What is the maximum value and minimum value of cosine x squared? The cosine of whatever I'm taking, what is the maximum value? Maximum value is 1, right? So, ignoring this side here, the maximum that could be is 1. 1 times x squared is always going to be less than or equal to x squared. The minimum value of this will be is negative 1. So this is going to be less than or equal to that. It's most likely equal. As they approach the same point. So if I take the limit of this as it approaches 0, and the limit of that as it approaches 0, if they both go to the same point, that is the limit of that function. What is that? 0. And the limit as x approaches 0 of x squared is 0. So my limit by the sandwich theorem is 0. X squared will always be above or equal to the cosine of x squared. Because the cosine can have a maximum value of 1. So cosine of 1 over x squared is going to be some value less than 1, right? So it's between the two at all times. At 0, we don't know what's going on with it, but we do know what's going on in these things. But I do believe if you graph cosine x squared, if you graph x squared cosine 1 over x squared, you're going to get something really nasty looking. Right around 0. If you're farther away, it's not so bad, but right around 0, it's a big deal. Okay. And I do believe, yep, that's it.